Hello and welcome to Module 5, which is an introduction to MapReduce. We're going to take the concept of MapReduce, we're going to split this into two different pieces. MapReduce is an important foundation on the way that Hadoop and distributed file systems work, especially how the processing works on these distributed systems. And what you'll find is that a lot of the other topics that we cover in this course, such as Hive, Pig, Spark, etc., are kind of built on MapReduce, or at least have some commonality with MapReduce. So understanding the basic concepts of how MapReduce works is actually really important. So we're going to split this into two parts. We're going to start by looking at the basic concepts behind MapReduce, how it works, the essential functionality, if you will, of MapReduce, how it accomplishes its goals. And then in our next session, we'll take a look at the coding specifically, so how we can create MapReduce applications that are running on the EMR cluster. So let's go ahead and start by taking a quick look at some housekeeping issues, and then we'll dive right into MapReduce. Let's go ahead and begin by talking about a couple of housekeeping issues. First and foremost, it's not on the slide, but I want to express my apology for not catching the typo in the book until I did. So I sent out the announcement and I did get a few questions about that. So hopefully that wasn't a big deal. I know a few of you tried to work through that with the 50 gigabyte versus 5 gigabyte file size, and you ended up with some pretty outrageous results. So that was not my intention. I apologize for that. So I will double down on making sure that I've more carefully looked at the wording in each of those assignments. I've been through all the assignments, but that one just kind of got by me. It didn't really kind of dawn on me what was going on. So I do apologize for that. And thank you for your flexibility. Hopefully everything worked out okay. I also did want to inform you that I did create the project groups this week. You probably saw this. I'll be posting specifics on the project requirements later this week. So just so you're aware, all the groups basically have at least 3. One group has 4. 3 or 4 is about the right number of individuals in this type of project group. The purpose for the project group is basically to take a data set and then using the various insights, the tools that we have available in the big data stack in order to gain some insights into that data set. It's not really an analytical project as much as it is just kind of showing your proficiency with the big data stack, the AWS EMR tool, and the other tools that we're going to be using this semester as well, like Pig and Hive and MapReduce and Spark and so forth. So I'll get into more detail about the actual expectations later. What I encourage you to do at this point is basically just introduce yourself to the other individuals in your group. Make sure that you're exchanging information, you are aware of who is in your group and so forth. So that way, when I actually release the project details next week, you'll have already gone through the process of acquainting yourself with your group. I also wanted to let you know that I think I mentioned this before, but I do have an open ticket with AWS Academy, their support, to see if there's any way we can retain state on those clusters better. I know that's frustrating for you. And I've got the assignment set up such that you shouldn't have to depend on state from one assignment to another, but it would be nice not to have to go through that process every time. So it's kind of interesting. I do have AWS experience. I think I mentioned this before, where that's not the normal behavior. Obviously, this is entirely driven by what's going on within our little sandbox. And it is quite an inconvenient behavior when you shut down the sandbox and the entire cluster shuts down and there's nothing you can do about it. So I'm going to go ahead and keep working with AWS. Fortunately, there's no assignment this week. So take a deep breath. This will give you an opportunity to kind of just focus on the meaning of MapReduce, not worry too much about what's going in your cluster. And worst case scenario, the next assignment is absolutely self-contained. So you can upload the files that you need and then walk through the processes right then and there. So we'll deal with that more later, but I just wanted to make sure that you are aware. Okay. Also, as I just mentioned, there's no assignment this week, so the focus is really on making sure that you understand the MapReduce process. And, since this is really at the heart of what's going on in the big data universe, everything is somewhat based on the concepts, at least, of MapReduce, which is essentially pushing the processing from a central processing server down to where the data is actually located. So we discussed this earlier, that in a traditional system, data moves from data nodes to some sort of central processing environment, where in a distributed file system and like a Hadoop infrastructure, it goes the other way around, where we're going to take the processing logic, we're going to push that down to where the data is actually located. So in this chapter, we're going to be looking at the process of how MapReduce works, and hopefully you get a better understanding of what makes this substantially different from the traditional systems. So let's go ahead and dive into MapReduce. Okay, so in a nutshell, what is MapReduce? Plain and simple, MapReduce is basically just a technique for distributed processing. The idea is that instead of moving the data from data nodes to some sort of central processing environment, we're going to be pushing the processing down to where the data sits, which means that we have to have some way of gathering up those results from each of those individual data nodes and then move that to a central location where all of those individual data results can then be collated and managed, and then hopefully get some sort of reasonable output as a result. So MapReduce contains a number of different phases, but we can generally break these down into what we refer to as the mapping task and the reducing task. So the mapping task is the process of identifying the specific data elements we want to work with on each of the individual data nodes, and then doing some sort of pre-processing, if you will, on those data nodes, so that we can extract the information that we need from an individual node and then move that over to some sort of other system that will, or other node that will be responsible for the primary work on the reduce task. So mapping, really, it's all about going to each node and finding the data that we're interested in, doing some sort of maybe manipulation or extraction or so forth. And that's going to be happening in a distributed way. So because the data is distributed across multiple nodes in our distributed file system, we can push those requests down to each of those individual nodes. Now, as you noted in our prior discussion about the allocation of blocks within the distributed file system and maybe doing some replication across multiple other nodes, what this means is that we actually have the flexibility of executing this on a variety of different locations. So if we've got a particular block that's replicated on, 3 different nodes, for example, then if one node goes down or a node is busy or something like that, that same data should be available somewhere else. And we should be able to push that request down to that particular node. So it's quite flexible in the sense that the name node that is responsible for identifying all the metadata and so forth is going to keep track of where all this data is physically located, know where to push that processing to, and then ultimately gather all that information back up again. So typical kinds of activities that occur in map task are things such as mapping, so the identification of data, combining, which is the process of collecting data or collapsing data into a single observation, and then partitioning. If you have multiple reducers, or if you trying to take that data and separate it into multiple segments for execution, then you may go through a partition process. So that's really what's happening at the map task. The important thing to note is that the map task, basically these things are happening on the actual data nodes themselves. After all of this work takes place, the results of that mapping, the entire map task process, are then going to be pushed off to another machine, another node, which is responsible for doing the reduce. So all of that data that emerges from the processing on each individual data node will then be pushed off to the reduce node, and it's responsible for other things like shuffling and sorting and reducing and so forth. So we'll talk more about each of these specific activities as we go through this discussion, but that's basically how this breaks down. So I think the most important thing to realize here at this point is the differentiation between mapping and reducing, where mapping takes place basically in the distributed model, where reducing, that's the point at which all that data gets migrated to a single location. That's where it all gets collapsed, and then we can do processing of all the collected data from all the individual nodes together. Ideally, though, we're going to be moving much less data from the data nodes to this reducer node, whichever one's responsible for that activity, than we would if we were using a traditional technique. Because traditionally, remember, the data is sitting on the data nodes. We have to move all of the data to wherever the processing is taking place, which is incredibly inefficient. So the whole purpose for this is to try to reduce the amount of data that we're actually having to move from the individual data nodes over to where the reducing activity takes place. And because we're reducing the amount of data and we're actually being able to do these map activities in parallel, this is going to be much, much more efficient, especially for extremely large data sets. Again, so the basic mapper tasks are usually things like, the most rudimentary, of course, is the mapper. So the mapper is responsible for identifying the values that we're interested in processing. Usually there's going to be some sort of key associated with that data. So identify the keys that we're interested in working with, and then there are values in the data set that are associated with those particular keys. So if you think of the idea as keys and values, that's basically what we're trying to do in the mapping phase. Like I said before, there are a couple of optional phases. Mapping has to happen because we need to know what data we're working with in order to be able to do anything effectively with it. However, there are a couple of optional phases, such as the combine phases. So if you have multiple occurrences of a single key and you want to collapse those into a single observation, that's really what the combine is all about. And then partitioning, like I mentioned before, if you have more than one reducer, or if you're trying to push results into two separate directions, for example, then you may need to partition those results in order to handle that. But the only phase that is absolutely essential is the mapping phase. The others are optional, but can be incredibly useful. On the reducing phase, there is actually some wonderful activity that you get for free, basically. The previous example, in previous diagram, we showed you basically how to do the shuffle and sort. And the shuffle and sort you get for free. That's actually happening by the system. So the idea is that once all that data is pushed from the data nodes to the reducing node, with the one that's responsible for that, it will automatically perform that shuffle and sort activity. And so basically what's happening here is it's organizing all that data based on whatever the key is and aggregating the data together based on those keys to give us a more useful presentation so that we can actually work with that data and effectively reduce it. And the reducer is basically what gives us our final answer, right? Collapsing all of that information into a single answer, a single response, or response stream so that we can actually get the results of our data processing. Let's take a look at a diagram that shows you this process in a little bit more detail. In this example, you'll notice that we've got a file called sales.txt. And the sales.txt file basically is nothing more than a transaction ledger. So every single time that a sale is made, an entry is provided in the sales.txt file, and then we're going to go ahead and process that file. This file, in this particular case, is actually distributed across two different nodes. So I've got node A and node B, each of which contain unique segments of the sales.txt file. So these are not replicants of each other. They're both different segments or fragments of the same file. So that means basically half of the transaction activity is going to be sitting on node A, half the transaction activity is going to be sitting on node B. And let's say hypothetically that our objective is to count up the total number of units that have been sold for every single product that we sell. As I mentioned in the first phase, the mapping activity, what we need to do is to identify a key and values associated with the data entries that we're interested in working with. probably the most effective key in this particular case, unless you do have an actual product key, is going to be the product name. So the product name in this case is going to be chai or sauce or tofu. And we also have a number here which indicates the number of units sold. Now that sales.txt file may have a bunch of other information available, but if we're interested in counting up the total number of units that have been sold for particular products, then the only thing we're really interested in is that number that tells us the number of units that have actually been sold. So this is the input file. The first step in this process is actually going through the mapping phase. So to identify the keys and the values associated with those keys. So we notice that the first line of our sales.txt file is a sale for chai tea, and there were 3 units sold. So we're going to go ahead and create then a key, chai, and then 3 is the value associated with that key. That's the number of units that were actually sold. Same thing with sauce 5, tofu 8. Here's another sale for chai, 9 units, tofu 1 unit, and so forth. And then the same sort of thing here in node B. We have keys and values. So the keys indicate the product names, and then the values in this case are the total number of units that have been associated with that particular sale of that product. So that's the mapping phase, basically just identifying the keys and the values. Now, essentially what we get as a result is a key and value list, right? There are multiple occurrences of chai, multiple occurrences of tofu, and so forth. And so there may be a combine phase that we want to code for at this point so that we can actually combine like keys or collapse like keys into single values. So for example, here in node A, chai tea, there's actually 3 units sold in this first line, 9 units sold in this fourth line. So that means there's a total of 12 units. So we can combine those counts for chai into a single line, and then do the same thing for sauce. There's only 1 for sauce, but there are 2 for tofu. And then down here in node B, we're doing exactly the same thing. We're just taking those values that represent keys, finding all of the values associated with those keys, collapsing those or combining them into a single number, so that what we end up with as a result of the combine process is a unique key for that node, and then the values associated with that key that represent the total units sold for that particular item in this segment of, in this case, the sales.txt file. So we do that here in node A. We also do the same thing in node B. Now, if you were going to go through a partition process, for example, if you had, like I said, multiple reducers and you want to send maybe some of the data off to one reducer, some of the data off to another reducer because you're going to handle them differently. Maybe you count tofu differently than you count sauce, for example. Then you could then partition these results into multiple partitions and then send them off to separate reducers. In our particular case, we're not really doing that, and so there's no partition activity that's taking place. So in this particular case, we're really not coding a partition. The output of the combine is going to be basically the output of the partition because we're not actually creating a separate partition. Now, ultimately, the whole idea is that all of this processing happened on this node. So data node A did all the processing that created this collapsed set of unique keys and then count values associated with those keys. Same thing on node B. All that activity actually happened at the data node itself. So that means that this data ultimately is going to have to be pushed off to some other server, some other node that can handle the process of aggregating the data that's coming from each individual node and then dealing with that in some way, however we want to handle it. So this particular line right here separates what's going on at the data node versus what's going on in the reducer node. So this is a separate node, node C in this particular case, that's responsible for doing all the reduce activity. The inputs to the reducer are basically the outputs, the aggregated outputs of all of the data nodes at the mapper stage. So that means that I've got my keys and key value pairs from node A, I have my key value pairs from node B, and so forth. Okay, so the next thing that happens is it goes through this shuffle and sort. Basically, it's going to take all of these inputs that it got from all of the various data nodes, and it can go ahead and sort those. So it shuffles them around, sorts them, and then basically what we get as a result of the shuffle and sort is a key value list. So while the outputs of the individual nodes were key value pairs, like 12 units of chai, 5 units of sauce, 9 units of tofu, and so forth, right? Here in the reducer process, the output of the shuffle and sort, which if you remember, we said we get that for free. That's automatic, right? Then that's going to be a key values list. So chai has 2 values associated with it, a count of 12 it got from node A and a count of 7 that it got from node B. Same thing with sauce, a count of 5 from node A, 9 for node B, tofu, 9 for node A, 6 for node B. So instead of a key value pair, it's a key values list. Now at this point, this all happens for free, and that's why we don't really concern ourselves with exactly what that shuffle and sort process is going to look like. We just know we're going to get that key value list as our output. So it's up to us now to decide exactly how we want to treat this value list that's associated with each of these keys. Since our logic was we wanted to add up the total number of units that were sold for an individual product, then logically what we're going to do is take these counts that are in this value list, add those together, and then associate those with the key. So in the case of chai, we'll take 12 plus 7, which is 19. That's going to be our output. So we have a key value pair again as a result of our reduce output. This is our final output. So we know that in the entire distributed data set, 19 units of chai were sold. 5 plus 9 is 14, so 14 units of sauce were sold, and 9 plus 6 is 15, so 15 units of tofu were sold. And again, the whole idea is that this represents the total counts for our distributed file. So in this particular case, we only have distributed across 2 nodes, but imagine if it was a very, very large file and you had this distributed across 40 nodes or 50 nodes. Okay, well, if that's the case, each of these 40 or 50 nodes is going to go through this process, doing the key value mapping, combining, outputting to a reducer. That means the reducer only has to look at the data that's the output data that's coming from each of these nodes. It doesn't concern itself with the granular, individual line items. It's basically only looking at the outputs, the list of outputs from each of these individual nodes. It shuffles and sorts those, and then we code whatever action we wanted to take on those values. So from a coding perspective, we have to code the mapping process. So that's the identification of what the key is and what the value is. So we have to identify that. And then we also have to tell it how we wanted to combine all of these things. And then we also have to code the reducer side. So once we get the key values list as a result of the shuffle and sort, we also have to code how we wanted to handle the values in that list, and that will give us our output. So let's take a look at another example using an actual data set. So this is a snippet from a file that has data from the Movie Lens database. There are 100,000 rows, and they basically represent user reviews. So each of these columns in the file represent different values associated with the user review process. So you have a user ID, which is the unique identifier for a particular user. You have the movie ID, which is the unique identifier for a movie. You have the rating, which is the actual rating that a user gave to that particular movie. And in this particular database, you have a timestamp. Now, this is just an example. Obviously, this data could be in a variety of different formats depending on how the data is stored and what we're trying to do with the data and so forth. So this is just an example. But in this particular case, we could do a variety of different things. We could, for example, find the average rating for a movie. You could sum up the number of ratings an individual user created. You could identify the average ratings that are given by a particular user. So there's a wide variety of different answers that we can generate from this single data set. You'll notice that the user IDs can repeat, so it is possible that a user could rate more than one movie. So you notice user 196 is repeated a couple of times, 186 is repeated 3 times. That's because these particular users have rated multiple movies. There's a potential of repetition, not only in the user ID. A single user could also rate multiple movies. So a movie could be rated by multiple users. So we could have repetition on the movie ID side and so forth. So I guess the first thing we have to do is to identify the task. What is it that we're trying to accomplish with this particular process, this data set? We're going to assume that our objective is to count up the total number of times that a particular user ID has rated a movie. So how many ratings did a user ID provide? Now, assuming this is a very large file, 100,000 rows, then it's probable that this file is going to be distributed across multiple nodes, and that a single user ID may actually appear in multiple nodes. So we have to assume that user IDs, since they can repeat, are not going to be found exclusively on one node or another node. Therefore, we're going to have to use this MapReduce process to be able to shuffle and sort and combine all of those values together. So here's our objective. How many movies did each user rate? So what is the total count of ratings that a user provided? And again, there's basically two steps in this process. First of all, the mapping step. The mapping step identifies the keys on each node in the cluster. So if our objective is to identify how many movies each user rated, the key is going to be the user ID, because that's what we're interested in. For each user ID, how many ratings have actually occurred. So we're going to identify the key as the user ID. Then we also have to identify the specific values that are appropriate for each user ID. Or in this case, the user ID is our key. Now, because we're doing a count, in reality, the value that's associated with the user ID that we're interested in is not actually even in our data set. Because each row in the data set contains the user ID, the movie ID, the rating, and the timestamp. But literally what we want to do in this particular case is just do a count. How many times does the user ID occur on each individual node? So let's go back to our sheet here. In this particular case, 196 occurs twice in this node. So that means the key value pair for this would be 196 and 2, because there are two occurrences of 196. 186 occurs 3 times. That user rated 3 movies. So we're going to have a key of 186 and then the value of 3. So there are 3 movies that are rated by that particular user. So you see how this works. Obviously, if my objective was different, for example, finding the average rating for a particular user, then I would want to get a list of all their ratings, and that way I could calculate the average by getting a list of all the ratings associated with that user. In this particular case, though, we're only interested in those counts, so we'll call that good. On the reducing side, the objective is to aggregate all those values based on key. So in node 1, for example, we might get 2 entries or a count of 2 observations or ratings for user ID 196, but maybe on node B, the second node, we have 3 other movies that user ID 196 rated. So it would be 196,2 for the first node, 196,3 for the second node, and so forth. So it's up to the reducing phase then to basically take these values, aggregate them together, and determine what we want to do with those results. So the objective in this particular case, since it's movies rated by users, we always have to ask ourselves these questions before we even start doing any coding, which is, what is the key we want to use? In this particular case, it's going to be the user ID. What is the value we want to use? In this particular case, the value is actually going to be a count of the number of occurrences of that user ID on each individual node. And then finally, what is the aggregation function we want to use? And that's going to be more on the reduce side, because our objective is to count all those up. So we've got our input data. That's going to be the prerequisite to the mapper. The mapper is the process of generating those key value results. And the output of the mapper that goes into the reducer is going to be key value pairs. So if you recall back to this phase, this output of the mapping phase is key value pairs, which already did some pre-aggregation. So it already went through the process of adding all of the, or counting all the occurrences of a particular user ID on a specific node. So the output of the mapper is a set of key value pairs. So the next phase basically is the reducer, right? So the reducer is going to take this output, and these are our key value pairs. So in this, if we're looking specifically at movie IDs, 196 has movie ID 242. Let's assume the movie ID was the value. We're going to count up the number of occurrences of the movie ID. So 196, 242, 186, 302, 196, 377. Let's say that the way we're going to identify the number of movies that were rated by a particular user is to essentially return the movie IDs that are associated with each user, and then just count up the number of movie IDs, distinct movie IDs that are associated with each individual user. If that's the approach, then this would be the key value pairs. Right? User ID and then the movie ID. Now again, you notice that user ID 196 occurs more than once. User ID 186 occurs more than once. So we're going to have to do some additional kind of condensation, right? We're going to have to collapse those values, and that way we can actually do something more meaningful with them. So here in the shuffle and sort phase, that's where we turn these key value pairs into the key value list. So 196, 242, 196, 377, those are two values for 196. Therefore, once we collapse those, we end up with 196 as the key and 242, 377 as the value. So we went from key value pairs to key value lists. So this is essentially what's happening in the shuffle and sort phase. So this key value list then is the input that we're going to use into our final reduce process. And so if we take this key value list and then simply collapse that by counting up the total number of entries in the value list, that will give us our counts associated with each key. So we know that 196 has two movie IDs associated with it. Count those up, 1, 2. That means that our final result is 2 for 196, 3 for 186, and so forth and so on. So this is a fairly simplistic example, but I think that it gives you a general sense of how MapReduce works. And at this point, that's the most important thing. Basically, just kind of get a sense for what's going on in the mapping phase, what's going on in the reducing phase, so that when we actually start writing code, we're going to be focusing on the execution of those activities that happen in each of these phases. You can code for this in a variety of different languages. The most common are probably Java and Python. You can use Java if you really want to. It's a lot more complex. There's a lot more code involved with Java. Python is substantially easier, and we're going to be using Python in this course to illustrate those coding concepts. When we get to that point, what you'll notice is that there are actually two separate structures that we code for. We code for the mapping activity, so essentially what happens within the mapper, and again, that mapper executes on each individual node. And then likewise, the reducing activity, what happens at the reduce level. So the code that will execute on the reducer, which is assuming to be operating on all those key value pairs lists that are actually coming from the individual mapped nodes. So we're going to go into more detail into that next week. But in this week, I just want you to take some time, think through this process, and make sure that you're comfortable with the basic idea of how MapReduce works. Hopefully this has been a useful introduction to how MapReduce works, and I think if you read over your course book as well, you'll be able to dive into more detail in specific areas. I think you'll get a sense for how it works overall. If you've got any questions or issues, make sure you let me know. Otherwise, we'll see you next week.